All right, so in this problem, we have two people. We have a man throwing a frisbee, and the frisbee's, oops, that's not going to work. Okay. So, man's throwing a frisbee, and the frisbee's got a constant velocity of VF. We've got a dog. Yes, I can't draw a dog, and I really can't draw on a pad, so that's even better. Oh, it's close enough. Okay, and it's starting with an initial velocity of 0, but it's accelerating, so it's got an acceleration of A. And the question is, if the dog doesn't reach its top speed, how much time in terms of velocity, the velocity of the frisbee and the acceleration of the dog, will the two actually run into each other? Okay, so as always, it's probably best for us to do a velocity time graph. So we take a look at my dog graph. My dog graph looks like this. I have velocity of the frisbee, and I'm going constant velocity. So the bottom line is it looks like this. And so if I wanted to find the area of this dog, the time they catch each other would be equal to velocity of the frisbee times time would be how far it went in terms of how far it was displaced. Agreed? Agreed. I'm talking to myself. Okay, so the bottom line is that would be because the area of the curve, and again, it's velocity of the frisbee going at constant speed, it's not accelerating, so it would look just like this. Now, if we're going to, oh, that was a dog. Oh, I totally messed that up. That's the frisbee, right? Sorry, everybody. Frisbee. Okay. All right, backing up. Now let's do the dog. Well, the dog is accelerating, so it has initially no velocity. In other words, standing nearby. Standing means it was stationary. It's going to accelerate like this. Okay. Now, here's the problem. I want to find the area of this. Now, I know a couple things. First of all, I know that the time it runs into it has to be the same as the time up here because we need them to be in the same place at the same time for him to catch the frisbee. So we know that's true. So we know that your area of the triangle in this case is going to be 1/2 t times, unfortunately, what's the height here? This is going to require some thinking. If the acceleration was, say, 2, well, then the acceleration would be at 1 second, the dog would be going 2 meters per second faster. At 2 seconds, he would be going 4 meters per second. At 3 seconds, he would be going 6, because he's going 2 meters per second faster every second. But I didn't give you 2, I gave you A. Well, if it's A, that means at 1 second, I would be going A, or A times 1. At 2 seconds, I would be going 2 times A. At 3 seconds, I would be going 3 times A. So at t seconds, I'd be going t times A, which means the top, the velocity at the end, is going to be t times A. T times A, which is also going to be the distance. Now we need these times to be the same, and we need the displacements to be the same. The good news is, even though it didn't give you displacement, so you can't use it in your final answer, these displacements have to be the same. If they're the same, I can set them equal to each other, which means the velocity of the frisbee times the time it's flying through the air has to be equal to 1/2 t squared times A. Right? Because they have to have the same displacement, so they must get to the same place at the same time. When the dog catches it. So the quickest thing to do is divide both sides by t. By the way, this says t equals 0 as a solution we're getting rid of. Does that make sense? Well, of course. The dog and the frisbee are together at t equals 0. We don't really care about that because we want to know when the dog catches the frisbee down the road. So to do that, we're going to figure out what time it would catch it. So we got to do velocity of the frisbee equals 1/2 a times t. I know I'm solving for the time, so I'm going to leave time on this side, move everything to the other side. I get 2vf equals at, or 2vf over a equals the time it takes for the dog to catch the frisbee, and that was the question at hand, okay? And so again, the approach was, I didn't have numbers, which is super rude, but I have velocity of the frisbee, so velocity of the frisbee times the time it takes for it to get caught by the dog is going to be how far it went. On the other hand, the dog, which is accelerating at A, it would have 1 times A at 1 second, 2 times A at 2 seconds, 3 times A at 3 seconds, so it would have t times A at its final time, whatever that might be. It might be any number under the sun. So with that in mind, the area here is going to be 1/2 because it's a triangle. The base, which is t, that's the time. And then the height would be the final velocity, which in this case is ta. So I put that all together. I recognize the two displacements are the same, set them equal to each other, solve, and I get this little gem. Again, it's a little early to do these variable ones, but I need to start showing them to you because they will appear a lot as we go along. We're using these more and more and more and more often. One of the strategies, by the way, we should remember is that when in doubt, use some numbers and figure out how the letters go with it, right? We looked at it and said, well, if I acceleration 2, I'd have 2, then 4, then 6. Well, that means that I'm going up 2 times the time. And so in this case, it would be a times the time. Okay? Super fast. Again, not the biggest concern on your list of things to worry about. The next problem is far more important. That's number 4. All right, problem number 4 is a traditional problem. It's a little bit more normal. We've done one very similar to it recently. And that's basically this idea, where I have a car accelerating between us when it first starts and then it stops by the next time it reaches the next light. So if I look at this, it starts off, the car is stopped, so I'm going to do a velocity time graph if I can. So the car is stopped, so time equals 0 at 0. It accelerates at 4 meters per second until it gets to 28 seconds. So at some point it gets to 28 meters per second. Now looking at this, I would say, well, at 1, it's at 4. At 2, it's at 8. When does it get to 28? If you can keep counting up until you get it, or you can simply say, oh, well, that must be 7, because 7 times 4 is 28. I draw that up. And I realize going up 4 each time, 7 times it goes up 4, it'll be at 28. Then it said it travels at constant speed for 15 seconds, so I go this way for 15 seconds, and that gives me a whopping 22 right here down the road. And then when I get to this point right here, it slows down at -2. Now, this is at 28 meters per second. So if it's at 28 meters per second, it's slowing at 2. It can go down 2 each time. How long it takes to get to the finish line? Well, the quickest way to do it is to go, well, it's going to take 14 times, losing 2 each time to get to the finish line. So that would be 36. Again, if you really want to, you could sit there and go, well, at 23, it would be at 26. At 24, it would be at 24. And you just count down until you get to it would be 0 at 36. All right, the rest is just the area of the curve, which is going to be 1/2. 7 times 28 plus another rectangle. It's a rectangle, and so that's 15. That is from 7 to 22 times 28, because that's the height. Plus, and then I got 1/2. Then I got the base is 12. The height is 28. And then I put that on my calculator. And I got 686 meters. I hope that's right. Feels wrong somehow, but let me do it right now. Sorry, pausing for emphasis, not really pausing so I can get my calculator. All right, the calculator agrees, so 686 meters seems like an appropriately good answer. So I'm going to save this and